For this second video on systems of equations, we're going to be looking at how to solve a system using elimination. Now, only the first two steps have changed from the other method using substitution. So steps 3, 4, and 5 are all going to be the exact same. So for the first step, we're going to look at the two equations and see if we can multiply each of the equations by a constant to get opposite coefficients on one of the variable. By opposite coefficients, I mean if one equation has positive 3x, we want the other one to say negative 3x. Sometimes it might even be set up for you. You might not need to do any multiplying at all, which is why I said if needed. So sometimes there's no multiplying, sometimes you just multiply one equation, sometimes you have to multiply both. It doesn't matter which variable you try to set up, it can be the x's or the y's, do whichever one's going to be easier for you. Once you've done that, you're going to add the two equations together, and then it should create a new equation that does not have one of the variables in it, which will mean that you can go on to finish solving to find what that x or y value equals, and then go back to substitution to find the second variable. So here's the example I'm going to work out. I have these two different systems of equations. Right now I do need to do some multiplying because I don't currently have a set of opposite variables on either of these, opposite coefficients. So my plan is going to be to multiply this first equation by 3 and this second equation by 2, because I'm noticing that then I would have positive 6x and negative 6x, so the x's would cancel completely. So here's my step 1 completed. The top equation was multiplied by 3. Make sure you multiply all of the terms by 3. And then my second equation was multiplied by 2. And again, I had to make sure I multiplied all of the terms by 2. My next step is going to be to add these two equations together now that I have set up a pair of opposite coefficients on the x's. So after adding these equations vertically, the x's canceled out. My 9y and 10y gave me 19y, and my 15 plus 42 gave me 57. So now I'm going to move on to step 3. I need to finish solving this equation. The solution will be pretty straightforward because all I have is 19 times y. So the opposite of multiplying by 19 is to divide everything by 19. So dividing gave me the answer y equals 3, which means I am now ready to move on to step 4, which was to take this value and substitute it into either of the equations. It does not matter which one you pick, so use whichever one you think will be easier. I'm going to substitute into the top equation in this case. These equations were pretty similar in complexity or size of the numbers, so it didn't really matter too much to me which one I chose, but you can see I chose the top equation. I replaced the y with the value 3 since I found these two things were equal to each other. So now for the last step, I just need to finish solving this equation for the other variable, the x in this case. So going through and performing my opposite operations to solve the equation for x, now I know what both x and y equal. So remember, this is making an ordered pair, and the idea behind this ordered pair is that this is the point where the other two equations cross each other. The lines for those two equations cross and meet at -2, 3. So the most common case for these is that you get a single solution, a single x value and a single y value, but now we're going to look at some of the special cases I mentioned in the last video. So here's what I showed in the previous video. Remember, we are identifying the x and y value where the graphs intersect. Most of the time there's only a single point of intersection, so one number for x, one number for y. But now we're going to look at some of these infinitely many and no solution cases. So the infinitely many solutions will be when I get a true statement like 0 equals 0 or 5 equals 5. The no solution case will be when my solving process leads to a false statement like 3 equals 8. Those are not equal. They are not the same thing. So here's my next example. I have the two equations listed here. I need to set up opposite coefficients on one of them. So what I'm going to do is I'm going to multiply this top equation by -2 because I'm noticing that that would make this a -2x, which would then cancel out the positive 2x from the other equation. Okay, so here's my step 1. I multiplied the top equation by -2. So you can see I got -2x, positive 6y, and positive 4. So the next step is for me to go ahead and add these two equations together. So when it came time to add, that's where the problems came in. I ended up on the left-hand side with both the x's and the y's canceling out, and on the right-hand side, I got a positive 8. But 0 doesn't equal 8, that's false. So what's happening is this is described as a no solution situation because these two graphs never cross each other. By looking at the graphs, you can see I have the two functions typed in here at the top. These two lines are parallel, which means no matter how far I zoom out, no matter where I look at on the graph, I'm always going to have the same situation. They will never cross each other, and that's why I ended up with that no solution situation. Okay, so now for one more example. Here I have, again, a system of equations. I need to start this solving process off by multiplying one of the equations by a number so that the coefficients will cancel. I want them to have the same number but opposite signs. So this time I'm going to multiply the top equation by 3 because I'm recognizing that then I'll have 12 and negative 12, which should cancel. Okay, step 1 is completed. I've multiplied the top equation by 3, so I got 12x, negative 15y, and 6. I did not need to multiply the second equation by anything in this particular case, so I left that second equation as is, because my goal is to get these x's to cancel. Next step, I'm going to add these equations together to cancel out the x's. Just as with the last one, my focus had been on the x's, but when we came to actually adding the equations together, I actually ended up canceling out both variables. And on the other side of the equation, the 6 and the negative 6 also canceled. So in this case, I got a true statement. Yes, 0 does equal 0. In fact, the number does equal itself. It doesn't have to just be zeros. It could be any number like 5 equals 5, 6 equals 6. As long as it's a true statement, you will say that there are infinitely many solutions. What's happening here is if I type these two functions into the graph, I'm going to see that they actually overlap. They're not two different equations at all. So here are the two functions we had in that last example. And on the graph, it looks like I only have one line. So you might be inclined to think that the other one is just farther zoomed out or something. But no, if I actually turn off the red line for a moment, I can see that the blue line is in the exact same space. So what's happening is we're not going to bother going through and trying to list every little coordinate that these have in common, because there's an infinite number of them. So that's why we're just saying there are an infinite number of solutions where these two graphs overlap, because they are in fact the same line in this case. So that's it for the lesson on systems of equations. We've now seen how to find a single point of intersection, or even maybe two or a handful of solutions. And then now we've also seen these two special cases of the infinitely many and the no solutions. So that's all for the concept of how to use elimination and substitution to solve a system of equations.